Hello and welcome to a Maths with Harry lesson. In this video, we're going to have a look at methods of proof. We're going to have a look at two proofs in this video. The first method is counterexample. You see it proof by counterexample, and to be honest with proofs, it's quite self-explanatory. It's in the title what the proof is. So this proof is you find a counterexample, an example that goes against what the statement is saying. If you're trying to prove a statement, then a counterexample is an example that disproves the statement, okay? It goes against what the statement is saying. So that's the first example proof that we're having a look at in this lesson. The second one is exhaustion. You prove something by doing lots and lots of steps, okay? Now, you don't have to do lots and lots of steps. You basically prove every situation. So if you're trying to prove something about even numbers, then what you might do is you might prove every even number. Not by testing every even number, but by proving it in a kind of a specific way. We'll get onto an example later on in the video. Okay, so let's have a look at the first example proof, and we're going to have a look at counterexample first. Now, I'm going to actually just do this through an example. I think that will be much easier. So, this is the example of a proof by counterexample. Example 1 says, prove that the following statement is not true. So we're basically trying to disprove this statement, okay? It says the sum of two consecutive prime numbers is always even. Right, it's always useful in a proof to break down what we have going on. So, we have the sum. The sum means addition. Okay, we're going to add two things together. The sum of two consecutive prime numbers. Okay, so we've got a sum, which means addition. We have got two, so we're adding two things together. And then we've got consecutive primes. Consecutive means when we list the prime numbers, they are together, they're next to each other. If they're consecutive, then if we've got, I don't know, 1 and 2 are consecutive numbers because they are integers, okay? They're consecutive integers because they're next to each other, if that makes sense, okay? So we've got two consecutive prime numbers is always even when we add them together, okay? So really, we want to do this, like it says at the top, by counterexample. Sometimes in an exam, you might not be told what method of proof to use. We're being told to use counterexample here. So what I would do is I would list all the prime numbers, and that's what we're going to do under this box. Okay, so here are the first 6 prime numbers. Prime number is a number that only goes into itself and 1. So we've got 2, 3, 5, 7, 11, and 13. Okay, and what we want to do is we want to choose two numbers that disproves this statement. And the statement is saying pick two prime numbers that are consecutive. When we add them together, we always get an even number. Now, straight away, I can see the first 2 prime numbers are consecutive because they're next to each other, 2 and 3. And I can see if we were to do the sum of those, so if we added those together, let's do that, 2 plus 3, that's quite easy. That gives us 5. Hopefully you can do that, okay? So we've added 2 consecutive prime numbers there. We've added 2 and 3 together, and we've got 5. Now 5 is not even. So if it's not even, then it's odd, okay? But what our statement says is if we sum 2 consecutive prime numbers together, it's always even. That's clearly not the case because that red 5 there disproves the statement. 5 is odd, okay? 5 is odd. So what we've done is we have found a counter-example. This example here, 2 plus 3, disproves the statement. Okay, it goes against what the statement is saying. So it's a counter-example. So hence, proved, or disproved, sorry. Proved the statement is not true. So we've proved not true. Okay, because 5 is odd. Now, it's always nice at the end of your proof to give a little statement or a little summary. Do it in more words than that, but that's the general idea. Okay, counterexample, find an example that is an example that disproves the statement. Okay, so here, if we're being asked that the sum of 2 consecutive prime numbers is always odd, then we could maybe find something here that is going to always give me odd. I don't know if that works. I was going to give me an even, sorry. I don't know if that works. I can see, oh yeah, 11 and 13, add those together, that is going to give me 24, okay? And then if we had always odd here, I've clearly shown that there is a counterexample that gives me even, okay? So if we flip that round to always odd. It's not, it's even, and so there's my counterexample. So that proves the statement is not true. In other words, it disproves the statement, okay? So there's an example of a counterexample proof. Here is another example. Now, part 1, or part A, is not really counterexample, it's just a proof, okay? Part B is where the counterexample comes in. So, if you want to pause and have a go with this one, please do, and then press play and we'll work through the answer. I'm going to start with part A by doing a little bit of rough working. Before you do anything with a question that has algebra in, what you really want to do is do some rough working to get to a statement from the algebra in the question, get to a statement that you know is true. Because that way, you can start off with that true statement, you just take that statement to be true, and then work your way back so that you finish with the thing that you're trying to prove. In the last video, we had a look at kind of the 3 stages of a proof, and we always want to start with a known statement or a known fact, okay? So I'm going to take this algebra, and here I'm going to do some rough working. The first thing I am going to do is I'm going to cross multiply on the left hand side. When I do that, I get x squared plus y squared divided by what's on the bottom when I cross multiply will be x times y, and I've not done anything to the right hand side, so that is still going to be a 2. Now, what I want is, I kind of want something that I know is true, and maybe you can recognise what I'm going to be getting here. I want to try and get to a bracket squared, because then, by doing that, I will have something on the right-hand side. I will have 0 on the right-hand side. Let me show you how I can get 0 on the right-hand side. What I'm going to do is I'm going to get rid of that fraction. Whenever you've got fractions like this, it might not be nice to have them, so get rid of them and see what algebra and what manipulation you can do. So, multiplying both sides by xy will give me x squared plus y squared is greater than or equal to 2xy. Then I can clearly see how I can now get 0 on the right hand side quite nicely. I can minus 2x from both sides. And I'm going to write the left hand side like this. X squared minus 2xy plus y squared is less than or equal to 0. Why have I written it like that? Well, because hopefully you can see that's an expanded form of a kind of generic squared bracket, and it's the expanded form of this bracket, x plus y squared. The reason for that is because we have an x squared from this term, we have a y squared from this term, and oh, actually it should be a negative. I apologise, it should not be a plus, it should be a negative because we took the 2 across to the left. So we've got still the x squared from this term here squared, the y squared from the minus y squared, and the minus 2xy from the 2 with the minus y and the x. Okay, so the more of these you do, the more you'll be able to realise, okay, this is an expanded form of this bracket, okay? And on the right-hand side there, we're still going to be greater than or equal to 0. So, I now have a statement that I know is true. And that's why the rough working before you even start the proof is really useful, because I now know that there's a connection between this statement here in green and the statement that I'm trying to prove. Okay? So what I'm going to do is I'm going to start my proof using this known statement. That's why this rough working is so important before you start the proof. So, I'll write here now proof, and I'll section it off. And when you start the proof, you want to make sure you show every single piece of working. One step should flow really nicely to the next step, and you shouldn't really miss anything out. So we're going to start with the known fact that we know, and the reason we know that this is true, you might be wondering, is, well, how do I know that's true? Surely that is just something that I got from the statement in the question. I know this is true because what we have is x minus y. Doesn't matter what x minus y is, okay? It depends on our value of x and y, but it doesn't matter what it is so far, because what we're interested in is we are doing x minus y and then we're squaring it. And we know when we square anything, it's always positive or 0. Okay, if x minus y is 0, then 0 squared is just 0. But let's say it's not, okay, let's say it's not 0. Anything squared is greater than 0. So that's why we know, oops, on the right-hand side here, we've got greater than or equal to 0 if x minus y is 0. Okay, so I know that's true because we are squaring something that's always going to be greater than or equal to 0. That's why I know that statement there is true. That is a known true statement, so I can start my proof with that. Okay, so what I'm going to do is I'm actually going to just work back on my rough working. This rough working is not going to be marked. I've done it at the side. This is where I start my proof. So now let's do the steps really explicitly. So what I'm going to do is I'm going to expand my brackets. Expanding them, I'm going to get this. I'm going to get the x squared term from the x times the x, and then I'm going to get minus the 2 from the power, and then times x and y, and then I'm going to get minus, a plus, because it's a minus times a minus, y squared is greater than or equal to 0. What you really could do there is you could actually write this statement and really spell it out if you wanted to. That's clearly equal to that, and then you could expand your brackets from there. Just because I've done a lot of practice, I know that when you expand this, you could do a shortcut. You can do this squared, you can do lots of these two multiplied together with the negative sign, and then the y squared as well. But if you wanted to, you could of course do the FOIL method there on the brackets if you liked. Okay, so now we have our expanded form, and I want to work backwards on my rough working, so I'm going to add 2xy to both sides to give me x squared plus y squared is greater than or equal to 2xy. Then divide by xy, we'll have x squared plus y squared divided by xy is less than or equal to 2. Let's expand this down here. And then, well, I'm going to kind of distribute that denominator to each thing on the numerator. So I'll have x squared divided by xy plus y squared divided by xy is greater than or equal to 2. And then I can clearly see the x squared will cancel with the x, and the y squared will cancel with the y, just to give me x over y plus y over x is greater than or equal to 2. And that is what we started our rough working with. Or did we want it? Hang on a minute. Yes, we didn't start our rough working with that. We cross multiplied. This is what, in the yellow here, we started our question with. That's what we were trying to prove. And so we have finished. We started with something that we knew, and we got that from our rough working. We then did some manipulation on the known true statement that we know. We did that manipulation, finishing up with what we're trying to prove in the question. Okay, part B says use a counterexample to show that this is not true when x and y are both not positive. Okay, so not positive. You might want to go through some steps or some combinations, and in an exam, I would really encourage you to do that, okay? Always try 1, always try -1, see what happens when you put 0 in. Of course, it's not going to work nicely here because we have got x and y on the bottom on our denominator, so 0 is not going to work nicely there. But always try different combinations, 1 and 1, 1 and 2, -1 and 1, see what happens. Let me tell you what happens if you try something along the lines of this, and I think this should work. If we have x to be -4, and if we have y to be 8. There are a few different combinations, and I think this one should work, because basically what we've got is we've got x being minus 4 and y being the negative of the double of this. If we double x and then take the negative so it becomes a positive, then we get 8. Okay, so you could have maybe minus 3 and 6. I think that works as well. But if we try that and see what happens, we're going to have on the left hand side minus 4 divided by 8 plus 8 divided by, let's make that a bit neater, 8 divided by minus 4. Of course, that is minus 1 over 2, minus a half, plus, and then we've got, well, it's not going to be a plus, it's going to be a negative, isn't it, minus 2. I can clearly see that is not greater than or equal to 2. In other words, we could say that is less than or equal to 2, because we've got minus a half minus another 2. Okay, so that clearly disproves the statement when x and true when x and y are both not positive. Okay. So I think you can do that. Actually, I'm just looking in the book. You can do that. They've done that here when they're both not positive. So yeah, just one of them not positive there. We've got the minus 4 not positive. Okay, so that is clearly a counter example because it goes against what the statement was saying. It's saying it's not true when this is the case. And of course, it's not true because we have proved it there with the counter example. Okay, so hopefully that makes sense about counter example. Now let's have a look at proof by exhaustion. And we're going to look at that just through a quick example. And then I think I have one example at the end. So proof by exhaustion says, here's an example proof. The sum of two consecutive square numbers between 100 and 200 is an odd number. I don't know whether this is true. I really don't. So what seems a sensible thing to do is just try every square number between 100 and 200 and find the consecutive square numbers and just sum them together. I don't think that's going to be too tricky. Then we've got every single situation of the statement, okay? So the first thing I'm going to do is I'm going to list the square numbers that are between 100 and 200. These are, well, we've got 11 squared, which is 121, 12 squared, which is 144, 13 squared, which is 169, and 4 squared, which is 196. No, not 4 squared, 14 squared, sorry. Yes, 11 squared, 12 squared, 13 squared, and 14 squared. So those are the 4 square numbers that are between 100 and 200. So an exhaustion proof for this is not going to be too exhaustive because all we're doing is just summing the consecutive pairs together. That's only 3 pairs. The first one we're going to do is sum those two together because they're next to each other. Then we're going to sum those two together because again they're next to each other in order, and then we're going to sum those two together because they're 3 consecutive pairs there. So let's do that. The first one we have is, I have there the squares. The first one we have is the grey. Okay, we've got 121 plus 144, and that gives us 265. So it gives us, because it's ended in a 5, it gives us an odd number. So I'll write there, that is an odd number. Okay, then let's have a look at the yellow pair, so the second and third square number between 100 and 200. We've got 144 and 169, and we get 313. Again, finishes with a 3, so that number is odd. So we're looking good so far because we're trying to prove that the sum of 2 consecutive square numbers between 100 and 200 is an odd number. That's what we're trying to prove. We're looking good so far. And then the third pair is the final 2, 169 and 196, and that gives us 365. So I can clearly see again that finishes with a 5, so that is odd. Those are the 3 situations. Those are the 3 possibilities of adding 2 consecutive square numbers together between 100 and 200. Every single possibility we had of the sum is odd, and so that is clearly a proof. We have done every single situation there, proved they're all odd numbers. Okay? Right, let's have a look at the final example for this video, I think. Yes, it is, and we'll prove this a little bit stricter. So, this one, you may have actually seen something like this at GCSE. Here, we're trying to prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. Why do I know that this is proof by exhaustion without doing it in this section of the video? Because it says all square numbers. I physically cannot prove all square numbers. I would never finish the proof because is there an infinitely many number of prime numbers? I think so. They're just going to go on forever. A square number, sorry. They're just going to go on forever and ever. We can continue squaring and squaring. So there's going to be many, never going to finish actually, square numbers. So how am I going to do this? Think back to GCSE, you've probably done something like this before. It's a proof by exhaustion, but in a little bit of a sneakier way without proving every single situation or possibility. Because we can't do that because there's just too many. There's infinitely many square numbers. So, pause and have a go, press play when you're ready for the answer, and I will work through it. Okay, so what I'm going to do is, I am going to cover every single square number, but I'm going to do it a little bit sneakily. The first thing I'm going to do is I'm going to consider odd square numbers, or square numbers that come from an odd number, sorry. So, what is a number? Well, let's just call it n. So, n is any number. This is how I'm going to start my proof. And this is quite a basic proof, so that's why we'll just say any number. Okay? If I multiply n by 2, then we know multiplying it by 2 will make it an even number. So 2n is an even number. So if I add something to that to make it an odd number, I just need to add an odd number, because if I have an even number and I add an odd number to it, I'm going to get an odd number. Now, the easiest odd number to add to that is 1. We know that 2n plus 1 is an odd number. Okay, and I'll just write odd. Odd number. Okay, so 2n plus 1 is odd because we've got an even plus 1 to it has to be odd. So those are the two possibilities. We're either squaring a even number or we're squaring an odd number. I'll start with odd numbers. So I'm going to take 2n plus 1 and I'm going to square it because I'm trying to prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. So let's take all of my odd numbers here and square them. Let's see what happens. The reason it's including all the odd numbers is because n is any number. So this can make any odd number. If I put n as 0 in, it will make the odd number 1. If I put n as 1 in, it will do 2 plus 1, which is 3. If I put n as 3 in, it will do 6 plus 1, which is 7. Okay, it makes all the odd numbers. So square it, all we're doing is expanding the brackets. We've got 2n plus 1 times 2n plus 1. And I get from that 4n squared plus, and I think it's going to be plus 4n plus 1. Yes, it is. That's what I get when I expand the bracket. Okay? Now I can see I've done a bit of expansion, but I can factorise also in a different way here. I can see the first two terms have two factors. They have a factor of n and they have a factor of 4. So let's factorise 4n out of the first two terms. That will give me n plus 1. And then we've still got that plus 1 that just carries down because we didn't factorise out from the plus 1. Okay? So what does that tell me? Well, I can't do any more factorising with that, and if I was just to expand that bracket again, I'd kind of end up where I started before I did that factorisation. But if you look here, we know that n is any number. So here I have some number times by some multiple of 4. So this here must be, let me do that a bit neater, this here is a multiple of 4. Hopefully you can see that. We have any number, n plus 1, times by n, but I'm not really bothered about that n. We're just multiplying this by 4. And so it has to be a multiple of 4, this under the red line there. Okay? If I multiply a number by 4, then the number that I get is a multiple of 4. That's exactly what I'm doing here. I'm multiplying n times n plus 1 by 4. So it's got to be a multiple of 4. So what we have is we have a multiple of 4 plus 1. Well, that's something that we're trying to prove. 1 more than a multiple of 4. This here is then clearly 1 more than a multiple of 4. All of that there is 1 more than, and I'll write 1 more than a mult of 4, because we have a multiple of 4 plus 1, so that whole statement there is 1 more, because we're adding 1 to a multiple of 4, 1 more than a multiple of 4. So there's half of the proof done, okay? We're saying all square numbers are either a multiple of 4 or 1 more than a multiple of 4. So the odd numbers, when I square them, always give me 1 more than a multiple of 4. And we can kind of see that. Did I have square numbers up here? Yes, I did, but let's do it with some easier square numbers. So let's take an odd number. Let's take 3. And if we square that, we get 9, and of course 9 is 8 plus 1, and 8 is a multiple of 4. It's 4 times 2. So there's an odd number squared. We always get 1 more than a multiple of 4. Okay? Right, so we've done the odds, so now let's square the evens. If I square the evens, I can just take 2n, because n is any square number, and if I times it by 2, I get an even number. Square that, I will get, well, 2 times 2 gives me 4, and n times n gives me 4n squared. I can clearly see, what is that? Well, that is a multiple of 4, because really what we've got is 4 times n squared. So this here is clearly a multiple of 4, and I will just duplicate that down there. Okay, that's clearly a multiple of 4 because we've got 4 times something. So when we do the even numbers and we square them, they are always a multiple of 4. Let's test it out. Let's do 4 squared. That is 16, and we can write that as 4 times 4. So that's a multiple of 4. Okay. If I do, I don't know, 8 squared, that is 64, and of course that's 8 times 8, which is 4 times 2 times 4 times 2. And of course there we've got a multiple of 4 in there, so 64 is a multiple of 4. It's also 4 times 16, but I thought I'd just do that easier. Okay, so you can always see that through examples, and here are examples that we've just done. These are all examples, and so are those, but that's not enough. You can only do a proof with an example if it's a counter example. If you've got one example that makes the statement false, then the statement is false. But if you have one example that makes the statement true, there may be a statement out there that it does, or an example, sorry, that makes the statement false. Here I've done a proof by exhaustion because I've proved for every single odd number and for every single even number. I've not just done 5 examples and said, yes, it's working, because, you know, the 100th even number might not be a multiple of 4. It is, but that's just an example, okay? If you do a certain number of examples and get them all right, they work. That's not enough to prove the statement true. You can only do a counter example to prove a statement is false. Does that make sense? Hopefully it does. So with an exhaustion proof like that, you will have to use algebra.